In the last lecture, we ended up with the concept of homeomorphic spaces. And two topological spaces are homeomorphic. This will be a topological space x, tx. Oops, I should make that a script t. And this will be a topological space y, ty, where of course what we're saying is that's the name of the set, and that's the topology on the set. And homeomorphisms only make sense in terms of topological spaces, right? It's a relationship between topological spaces. So you have to establish a topology. Whenever I draw this sort of round circle, and we'll be doing this a lot, I'm talking about a set X, and in this case with a topology, but it could be anything. I mean, it could be you know, these line intervals we did last time. I could be talking about that. I could be talking about maybe just a finite segment of the plane. I could be talking about the infinite plane. It really doesn't matter. But whatever it is, it's a set that has a topology and that follows all the rules we described before. Then, of course, we learned about continuous functions, right? Any function, there's going to be some kind of inverse mapping, and the behavior of the inverse mapping tells us whether the function is continuous. And then if the inverse mapping is in itself a continuous function, which basically means that the function itself maps open sets to open sets, and of course the inverse function maps open sets to open sets, that means it's bicontinuous, and it has to be 1 to 1 and onto. So if it's 1 to 1, let me write that a little better, and onto, and it's bicontinuous, then we have this whole thing is a homeomorphism. And the reason this is important is because in some sense you can argue that topology is really the search and the study of things that are invariant between homeomorphic spaces. And what do we mean by that? First of all, how do we know a space is homeomorphic to another space? Well, the answer is if I can find any homeomorphism that connects the two spaces, any single function that's 1 to 1 onto and is continuous and has a continuous inverse, right? If I can find any single function that does that, then the two spaces are homeomorphic. That's the relationship. They are homeomorphic. Now, there's a lot of functions in the world. There's a lot of options to take for these functions. And it doesn't matter that all of them are 1 to 1 and onto and continuous in both directions. Only one. If I can find any single one, then the two spaces are called homeomorphic. And then the reason that this is important is because every topological property of this space is going to be the same as the topological properties of that space if I can even find a single homeomorphism. Likewise, if I discover that there's a topological property of this space that is not the same as that space, then I know that no matter how hard I look, I will never find a homeomorphic function connecting the two. In fact, the way you typically prove that x is not homeomorphic to y is you show, for example, oh, this x is second countable, but y is not second countable. Well, second countability is a topological property. If y is not second countable and x is second countable, then they are not homeomorphic, and I will never find this function f to I'll never find a bicontinuous 1 to 1 and onto function f. So in many ways, the idea the topological properties we've talked about already are countability, right? We talked about countability, and we talked about separability, and we've talked about continuity we talked about, but we did that in order to help us understand what a homeomorphism was. So I think these are the two big ones we've spoken about. I also want to cover compactness, right? And probably connectedness is an important one too. Let's see if we can cover these two today. what's important to understand is there are many, many kinds of countability. I'm sorry, many, many kinds of separability. I talked about T0, T1, T2. I talked about regular, and I talked about normal, right? We talked about those a little bit. But that's just 5. There's probably 25 different versions of separability. There's a lot of different versions of compactness. There's at least 2 versions of countability, but there's probably more. You know, I'm no super expert on this subject. The point is that no matter what version you have, no matter how subtle a type of separability you have, X, the set X and the set Y will share the exact same separability if they are homeomorphic. Right? That's really important. So the homeomorphism is kind of interesting because what you're seeing is that open sets are mapped to open sets in both directions. And you can imagine that what this is basically saying is I'm taking the set at space X, and I take every open set in the topology, and the function is kind of changing it, right? The function sort of taking this open set and is kind of mutating it into some other open set. And likewise, the open set here is getting mutated by the inverse function into this. And that is why homeomorphisms are so interesting. These homeomorphic maneuvers are just really deforming the topology. The topology of X is being deformed into the topology of Y. But likewise, that wouldn't be good enough because you could lose sets, right? Or you could have 2 topological sets that kind of get squeezed into one or some weird thing. But if likewise the topology of Y gets morphed into the topology of X through the inverse function, then what you're really doing is you're just sort of changing the shape of things. And this is the point set topology foundation for the old famous fact that a donut, oh, that's a bad donut. Wait a minute, let me look at this donut again. A donut, remember that old story? A donut, a donut, equals a coffee cup. Remember that whole thing? I'm sure you've seen it before, where a donut and a coffee cup both have a single hole, right? They both have one hole. Well, they're homeomorphic, right? Because you can create a function that takes every point of this donut and finds a corresponding point of the coffee cup. Every open set that you might establish on this donut, that you would make the donut some kind of topological space, that open set will mutate into some sort of open set on the coffee cup. And that is a homeomorphic maneuver. Likewise, you go back, if you can do it in both directions, you can deform the coffee cup back into a donut. Yeah, if you can only do it, a continuous function will let you take a donut and turn it into a coffee cup, but it won't let you take the coffee cup and bring it back into being a donut, right? That unless the inverse function is also continuous. And that's, of course, the definition of a homeomorphism, right? The function and the inverse function have to both be continuous. You can also imagine why the one-to-one and on-to is important. Every point of the donut's got to have a point on the coffee cup, and every point on the coffee cup has got to have a corresponding point on the donut. And you've got to be able to cover the whole coffee cup with the whole donut. That's the on-to part. So homeomorphisms is this notion of, it's the weakest notion that connects two sets. There's no real geometry in here, right? There's no metric, right? And there's no sense of shape, really, right? All there is the topologies. And increasing levels of specificity start growing the way these deformations are allowed, right? For example, you can imagine we might have a rule, no, I want to take squares only to parallelograms, right? Well, the notion of the shape of a square to the shape of a parallelogram, that's all geometry, right? There's no geometry in topology. There's no geometry with a homeomorphism. This geometry here that would take a square to a parallelogram, that has the notion of an affine transformation, what's called, right? And in order to get that, we have to understand a lot of other things that make up geometry. Topology is the geometry without all the measurement, right? And that's why it's so fundamental. Now, geometry, all the strictures of topology will exist in geometry, but it's not the reverse, right? It's not the reverse. So in order to do these kinds of transformations, you have to have some other notions of mathematics. Now these functions, on the other hand, you don't necessarily have to have that. In other words, you don't have to be able to measure distances here, or structures of shapes here or here. You may, but you don't have to. And a lot of the examples we do, you actually can. Like when I talk about the plane, and I say, oh, we're going to talk about like an open rectangle, which we'll do in a moment. Well, obviously I'm talking about perpendicular lines and things, but that's just to exemplify the principles of the topology. You don't absolutely have to do it. Okay, so that's in general why homeomorphisms are important, and they will be important when we discuss manifolds. Now let's talk about compactness. Actually, I'll just erase the whole thing. So the notion of compactness is that it's a topological property, which means the definition of a topological property is that two homeomorphic sets will share the same topological property. So compactness. It's actually a bit subtle. It's certainly not intuitively obvious. First of all, we're going to talk about our topological space will be the plane, R2, with the usual topology. And I'm going to ask the question about one particular subset of the plane, and that's this rectangle. This rectangle is a subset of our topological space, and I'm going to ask the question, is it compact, right? Is it compact? And we can ask whether the entire topological space is compact, or we can ask whether a subset is compact. So first we'll talk about this subset. Well, in order to understand compactness, I have to be able to start building covers. And a cover is one of the few things in this subject that means exactly what you think it means. It's a set of an open set in the topology of the plane that literally covers the set in question. The set in question I'll call it it'll be called X, right? So the set in question is X. So I need an open set in R2 that covers X, and that's easy. I'm going to draw my open sets with solid lines now, all right? Just so I can make it a little easier. However, we always understand we're dealing with open sets, and in the normal topology of R2, those open sets do not include their boundary. And X, by the way, is open in R2 because it's a rectangle that doesn't include its boundary. So the set in question is this set, which is a rectangle which does not include its boundary, which also happens to be an open set, right? A rectangle that doesn't include its boundary is an open set in the usual topology of R2. And here's an example of an open set in R2 that completely covers our set. And what's interesting, nice about this is that the number of open sets I need to cover X is 1, right? I need only 1. And there's a lot of possibilities out there. I could have this one, or I could have a nice rectangle that's just a little bit bigger, or I could have the whole plane. The whole plane would be. But I can, in this case, I have one open set that covers the set in question, X. Of course, I can obviously do this with 2, right? I can take a rectangle that covers about half, then an overlapping rectangle that covers the rest, right? So I can do it with 2. I can do it with obviously 3 or 4 or any number of open sets to cover this rectangle. Now, in all of those cases, 1, 2, 3, etc. to n, it's a finite number of open sets that are covering our rectangle. But I can also make a construction that covers it with an infinite number of sets. That means I need an infinite number of sets to complete the cover. And that construction goes like this. I'll cover half of it with this rectangle. Then I'll take the next rectangle, I'll overlap a little bit, and then I'll go halfway again. Then I'll take the next rectangle and overlap a little bit, and I'll go halfway again. Then I'll take the next rectangle, overlap a little bit, and go halfway again. It doesn't matter that these sets have points that are not in the set in question. It only matters that the set in question is ultimately a subset of this. So if I take the union of all of these open rectangles, remember these are open sets. This isn't, by the way, I'm looking for something called an open cover, I guess, because all of the sets I'm using to cover my set in question must be open. So I can do this forever and ever and ever and ever, and I will come arbitrarily close to this boundary. But any point, if I just sort of go in there and I blow up, say I just blow up this boundary here, I just zero in on it, what will I see? I'll see the open end of the set in question, and then an arbitrary point arbitrarily close to that. Well, eventually, I'll find one of my open sets in this scheme of mine that has an infinite number of these things. Eventually, it'll be in one of them, and it'll be covered. And so all the points, as they approach the boundary, will eventually be covered by this scheme. And I don't have to worry about the boundary, because the boundary's not in the set, right? The set in question X doesn't include its boundary. So that is a case where I have an infinite number of sets that cover my open rectangle. Now, that's not the only way to cover it with an infinite number of open sets. If this is that same open rectangle X, I could literally just tile the plane. The entire plane, I could just tile it with open sets, right? Tile it with rectangles forever and ever and ever in all directions, right? And the whole infinite plane is tiled. And there's an infinite number of sets, and the union of that infinite number of sets happens to be the whole plane, but that union definitely covers this, our set in question. So that's another way of having an infinite cover. Now, this is a little less interesting, you might think, because heck, I've included some open sets in this cover that don't have any intersection at all with the set in question. But it doesn't matter. It's still a cover. It's a cover because the union of all these sets contains our set in question. But you're right if you ask that question. This condition here seems to be different than this condition here. They both are infinite covers, but this one has the advantage that there is a finite subcover, meaning some finite subset of these open sets, some finite union of these open sets actually completes the job. And in fact, in this case, it would be, say, 1, 2, 3, 4, 5, 6. Right? There's actually only 6 open sets that I really need in this cover to cover my set. It's still an infinite cover, but it's got a finite subcover. What's important is that in this case, it's an infinite cover, but there is no finite subcover. You actually need every single one of this infinite set to cover this set. And there's no other way to do it. There's no other way to do it. So this set has no finite subcover that will cover this cover, right? This cover that I've constructed has no finite subcover that actually covers the set. You need every one of them. And that notion, that distinction is the core idea that defines the idea of compactness. And it goes like this. If I can find any cover with the property that there is no finite subcover, then the set is not compact. I only need to find one. So for example, this set is clearly, X is not compact because I found one. I have found, by construction, I've constructed a infinite cover that has no finite subcover. So X is not compact. And that's kind of interesting because you're looking at X and you're saying, well, it's just sitting there in the middle of the plane, right? How can that not be compact in some sense? It's just a tiny, tiny piece of the infinite plane. I can clearly cover it. I can definitely put a circle around it. Not good enough. To be not compact, you actually have to be able to show that there's no infinite cover that doesn't have a finite subcover. So that's as a good idea to sort of think about how that might work, let's consider a closed rectangle. That would be the same open rectangle, but the closure of it, so it includes its boundary points, right? So in this case, my solid line actually does mean a closed set. So now I have to go back to dotted lines for my open set. Well, now my construction is going to totally fail, right? Because I'll go halfway with this rectangle, then I'll do an overlap here, I'll go halfway again, and then I'll just, keep I've got the same process, but here's the problem. When I get towards the end, right, and I'll go ahead and blow that up again. When I get towards the end, I can take arbitrary points close to the boundary. I'll catch every one, just like before, right? I'll always eventually find in my proposed cover, I'll eventually find some open set that's part of the cover. That cover will eventually overtake every point, no matter how close I get to the boundary. The problem is by this construction, the boundary point itself, they'll never be part of this construction. There's never, no matter how close I get to this line, I never get that line, and that line is part of X, right? So this line is never inside this so-called cover. In fact, it's so-called cover because it's not a cover at all. It's not a cover until it gets this line. Now you realize, well, I need to dip into my topology, the topology of the usual topology. I need to find an open set that includes this line as well. Well, whatever it is, it's gonna look like a rectangle, and that rectangle is gonna cover that line. The line can't be on the border of the rectangle. The line's got to be in the interior of the rectangle, because the rectangle is an open set. As an open set in the usual topology, it doesn't contain its boundary, so this line has got to be in the interior of that set. Well, once that's the case, then the interior of that inner line, or the interior of that final rectangle, eventually it's going to merge with this process that's going, no matter how thin a rectangle I choose here, eventually my proposed cover is going to overlap it. And when that happens, we're done. We've got a finite subcover. It could be gazillions of open sets in it, but it will be finite. And so suddenly, my set in question is now compact. And it's compact. As soon as it owns that boundary, you'll discover there's no way that you can create an infinite cover that has no finite subcover. And what's interesting about it is that it doesn't seem like it's a heck of a lot different than the last case. But for compactness in the usual topology of the plane, that's all the difference in the world. That's all the difference in the world. You'll notice, by the way, that these points on the boundary, right? These points here on this boundary, and on that boundary, they're fine. They're inside the construction just fine. It's only this last one that doesn't make it in. And I'll let you think about it yourself, but think about how you might use an open set in the regular topology of the plane to get all of these boundaries in, because there's many different ways of doing this, and still create some kind of infinite cover. And you shouldn't be able to do it. So that's compactness. Now there's a lot of different variations on compactness, and some sets can be non-compact in different ways. Some sets can be extremely compact, more compact than others. We're not going to go through all of them, but whatever type of compactness you're dealing with, it's preserved by homeomorphic relationships between topological spaces. All right, so now then there's at least one other topological property we should talk about, and that's connectedness. Connectedness has a lot of definitions, and we will probably have to cover at least two, just because it's inevitable that you'll see them both. And look, this isn't going to be a detailed discussion of connectedness, because this isn't really a course on topology. This is something to get you sort of comfortable with the words, so when you study topology more closely, you won't have much trouble, but at the same time, it's enough to understand manifolds. So here we have a topological space, X and Tx, and here we have a topological space, Y, and Ty. And again, I'm writing down circles, but I'm referring to any kind of space. The thing here is that, look, now I've got two circles, right? So this topological space X, I'm going to say, is actually the union of G and H. And I'm also going to say that G and H have no intersection, right? So X is the union of G and H H has no intersection, but also G and H are open sets. So G and H are elements of the topology of X. So if that's the case, if this definition is met, then X is not connected. X is disconnected. Now, if it could have GH and I, by the way. I mean, there can be an unlimited number of these things. The point is, though, as long as you have two, as long as this is satisfied for at least two, you have a disconnected set. So the idea now is that being a topological connectedness, being a topological property, means that my function f with its inverse, f inverse, is going to ultimately, because connectedness is preserved under homeomorphisms, if I say that there's a homeomorphic space y out there that's homeomorphic to x, I'm going to say that y has two disconnected components, f of g and f of h, and they satisfy these same rules, namely f of g union f of h equals y, and f of g intersection f of h is the null set, and f of g f of h, and this part is the continuity, f of g f of h are elements of the topology of y. And of course this is basic notion of continuity, right? This f is an open mapping. F maps open sets to open sets. F inverse maps open sets to open sets. And so because it's a homeomorphism, right? And don't get wrapped up on the fact about, remember, all I have to do is show that there exists an f with this property. X and y aren't homeomorphic because I've chosen a certain f. X and y are homeomorphic because there exists somewhere an f that has this property. I could be considering non-continuous functions or functions that are continuous but not homeomorphic between x and y. That's fine. I'm allowed to talk about continuous but non-homeomorphic functions between x and y. But x and y will still be homeomorphic because somewhere out there exists this function that is indeed homeomorphic, and if only one exists, then the spaces are homeomorphic. So I could talk about another function, g, where g has an inverse mapping, and the inverse mapping maps open sets to open sets, but g does not. Therefore, g inverse is not a continuous mapping, and g is not a homeomorphism. But I can still talk about it. It's a continuous function. G is still continuous, which has very nice and important properties. It's just not as intense as f is, because f is a homeomorphism. But x and y will forever be homeomorphic, regardless of what function you're studying. All you need is to prove that such a function exists. Okay, so that is connectedness. Now there's another type of connectedness called path connectedness we should talk about. And path connectedness is a little bit different, and there's a lot of details about path connectedness we're not going to discuss, but I want you to understand that path connectedness is another way of understanding connectedness. So in the plane R2 with the usual topology, I have 2 points, little x and little y. And that looks like a G, doesn't it? Little x and little y. And I draw a line from x to y, and that line is totally inside the set. So x and y are path connected because I can create this line. Now when I say I've gotten a line, remember I'm talking about the plane R squared, so it's easy for us to talk about a line. But in an arbitrary set, it's a little more abstract. What I have to prove is that there's a map from the line segment 0 to 1, right? So that would be the segment of the real line from 0 to 1, that there's a map from that into the set X. And that map I might call F, and it's got to be continuous. It's got to be a continuous function from the line segment 0 to 1, which including the endpoints, into the topological space in question. And that continuous function has to have a few properties, like f of 0 must equal x, and f of 1 must equal y, and it must be continuous. Right? It doesn't have to be homeomorphic. Remember, here homeomorphism would be too much. I'm not saying that this line segment must be homeomorphic to the space. I'm only saying that there's got to be a continuous function from the line segment to the space such that f of 0 is the point x, f of 1 is the point y, and the continuity assures this sort of line-like nature regardless of what type of set the set is. All right? So if I can do that, then I can say x and y are path connected. And if I can do that for any x and any y inside the space in question, x, the topological space in question, then x is path connected. And if x is path connected, then path connected, by the way, inherits connectedness. The connectedness that we talked about before, where we said a disconnected set looks like that. Clearly, this is not going to be path connected. You're never going to be able to create a continuous function from the line segment to this that connects x and y. That's not possible. So path connected, it turns out, you can prove that if you're path connected, you are connected. What's interesting is it doesn't go the other way. If you're connected, you're not necessarily path connected. And the legendary counterexample is the function f of x equals 1 over sine of x, right? If you don't know about this function, you've got to learn about it right away, because 1 over the sine of x, clearly, as x is approaching 0, this, what am I doing? Sine of 1 over x, right? The sine of 1 over x. As x approaches 0, right, 1 over x approaches infinity, and then the sine just oscillates like crazy. So this thing is basically oscillating infinitely on its way to 0. And it turns out that that is a connected set. That's the graph. This graph has the property of connectedness because it goes across 0, right? It's connected, but it's not path connected. It's a famous counterexample that you can look up about this. So path connectedness is actually very interesting. However, there is one little thing about path connectedness that is important to sort of gather. Imagine that we have this set, and along with that set, we're studying two different topological spaces, say x tx and y ty. Well, y ty, let's say y looks more like that. It has this hole in it, right? So this is not part of the set, right? All of this is part of the set. All of this is part of x. All of this is part of y, but that's not part of y. Well, it's interesting because in this case, they're still both path connected, right? Any two points in x can be connected, and any 2 points in y can be connected, right? Any 2 points can be connected. But in y, there's this other question. What about a path? There's something fundamentally different about the paths I've drawn in blue and this path I've drawn in red that kind of goes around that hole. And there's actually something fundamentally different about the path I've drawn in red with the path I've drawn in green, which goes around the hole like 10 times before it goes there. So this is they're still both connected. The reason I'm demonstrating this is because this hole causes problems, and it distinguishes between these different types of paths. And the explanation is that this path cannot be continuously deformed into these other paths. This red path can never be continuously deformed into the green or blue. The blue can never be continuously deformed into the red or green. And likewise, the red can't be deformed into the blue or green. So that distinction between these types of paths leads you down to the subject of homotopy. And homotopy leans heavily on continuous functions, because you basically have to create, to study the theory, right, you have to create a continuous function that takes this path and continuously deforms it into this path. So we're taking a continuous function that deforms paths and functions, and it can be done. It's not very difficult. You just build up on this subject of continuous functions, and you can create homotopies. It's really not a problem. But the point is in this set X, there is no need for this. All paths are homotopic. Every path can be definitely deformed into every other path. Well, actually, I should say every path between any 2 points can always be deformed, no matter how much loopiness it does, can always be deformed in every other path. And the reason I've gone all my way to talk about this is because you'll see the word simply connected. If you're path connected and you do not face this problem of having different homotopies, different homotopy classes of paths, then you are simply connected. All the paths can be deformed together. Now there's another related word that comes up a lot that you shouldn't confuse this with, which is homology. And that word has to do with a different aspect of how paths can be manipulated and also how spaces can be cut. For example, in this case, I can cut y in one place and everything remains connected, right? Even if I cut y right here and separate all of this from all of that, all these points are still going to be connected. In that case, they'll all be simply connected, by the way. But if I tried the same trick here, if I cut the space here, well, I've disconnected it. I've actually produced two separate disconnected components. So I can't cut this one at all without disconnecting the space. Here I can cut it once. If there was another hole, I'd be able to cut it twice before it was disconnected. Okay, but so we're not even going to touch on homology, but homotopy is kind of interesting because it helps us understand the notion of simply connected. Okay, so ultimately now, that is where we're at. Is we now understand the idea homeomorphic function. I only need to draw it one way, but a function and its inverse, spaces x and y are homeomorphic if you can find a single homeomorphism, and it preserves all of these key properties we've talked about: separability, countability, compactness, connectedness. All of these things are topological properties because homeomorphisms preserve it. And homeomorphisms are important because they are mapping open sets to open sets in both directions for a given function, which has to do with the idea of deformation. We're just deforming things. But all this is topology, so we really have no notion of shape, no notion of distance, no notion of measurement. Some say, yeah, there is a notion of measurement. The topology itself is a notion of measurement. A continuous function, if I'm in an open set here and I've got 2 points, a continuous function should map that open set to an open set here that also contains the image of those 2 points. You shouldn't be able to separate 2 points that are in an open set. You shouldn't be able to take that open set and separate points by graphing it into other points using a continuous function. Anyway, those are the basic properties of the topological spaces that we're going to be talking about. Those are the basic properties that are most commonly referred to when you refer to homeomorphic spaces. And now I do believe we are in a position to study manifolds, and that will be our next lecture.